and I hope you will find it interesting. So if you have any questions by the end of the session, please do not hesitate to text us directly on our page or leave a comment below, and then we're going to track that down and get back to you as soon as possible, okay? So once again, today is grade 12 physics, which will focus strictly on work and energy, for grade 12 learners. So we hope you guys are ready. Now we're about to begin in less than few seconds. Actually. So we are about to start. Channel for more sessions. And do not forget to like our various social media platforms such as Instagram, Facebook, Twitter, and also LinkedIn. We hope that this session is going to be thought-provoking and very informative for your sake. This session is brought to you by Blended Academy, and we are happy to have you here. Thank you very much for joining today. It's a very beautiful Sunday afternoon. We hope you do have a great day and a blessed one. Thank you.
All right. Thank you for joining us, guys. Welcome to the lesson. Welcome. It's physics, just like they've mentioned. We're doing physics for grade 12 learners, focusing on work and energy. So it's work and energy. This is what we're going to be covering today in this lesson. And also, just to remind you guys, please take out your notepads, notebooks, and also pens and calculators, just take them out, get them ready, because we're about to begin with the lesson now. All right, let's start off with the basics, defining what work is, and also the work energy theorem. We're also going to cover what we mean by energy, or what is meant when you talk about energy, and different SI units when you talk about work and energy. So now to start off, we're going to have some basics covering work. So now you need to remember that work is a scalar quantity. So now this quantity only has magnitude. So when we're talking about scalar quantities, we're talking about quantities that only have magnitudes but no directions. So you need to remember that. And I'm sure most of you learned this in grade 11. So you guys should be able to recall this. So now a scalar quantity has no direction. So it's magnitude only. That's a scalar quantity. So we don't have directions here when we're dealing with scalar quantities. No direction. You understand? And also the SI unit of work, which is also the SI unit of energy, is joules. So now guys, it's very important for you to put in your SI units when you dealing with different problems involving work and energy, because there's actually marks for putting in your SI units. So you need to be very careful when it comes to that. So whenever you write your final answers, please remember to put in your SI units. So which is in this case, we're dealing with work. So we're going to have to put joules at the end of every final answer when we reporting this quantity. You understand? So now let's go on to the concept of network. So now this is also very important in this topic, because we're going to deal with the work energy theorem. That's where we're going to be able to apply this network, or this concept of network. So now network just means the sum of all work done on an object. That's your network. You understand? Not like your Cell C's, Vodacom and all that. This is a different network, you understand? So you need to be able to differentiate between the network that you're used to and this one that we're going to be dealing with in physics. So now it's the sum of all the work done on an object. And also it's a result of net force. So this network is a result of the net force that is acting on that object. Result of F net acting on the object. You understand? So maybe if you're given, for example, if you're given the F net the net force, and then they want you to calculate the net work. You just need to multiply your net force and your displacement, and also the angle between your work, or the direction of your work, and your force. You understand? So now let's continue, guys. Let's move on to positive and negative work. There's positive and negative work. Let me just put it down here as number 1. So this is positive work. Positive work. So now this is the work done to move an object in the direction of the force. Work done to move the object in the direction of the force. So now what this means is that if you're pushing an object towards the right and that object moves towards the right, that means you've actually done positive work towards the right. You understand? So now it means you're pushing the object towards the right, and if it reacts towards the same direction, that means you've you did negative work on that object. Positive work on the object. Sorry about that. And now this positive work increases the kinetic energy of the object. So now you're going to have an increase in kinetic energy when we're dealing with positive work. All right. So now, and then number 2, we've got negative work. So now this is just the opposite of positive work. This is the work done by an object or by an opposing force. Work done on an object by an opposing force. So for example, let's say you're pushing an object on a rough surface and then there's friction there. So now remember that friction always acts in the opposite direction of the motion. So friction is going to give you negative work done on an object. You understand? Because it's pushing in an opposite direction. So it's acting in an opposite direction to the motion of the object. All right. Now this here, negative work decreases the kinetic energy of the object. You understand? So it's very important for you guys to be able to remember or distinguish between positive work and negative work. You understand? So now let me just draw a small drawing here to demonstrate the effects of work, or the effects of positive work and negative work. So now here in this diagram, I'm just going to demonstrate to you positive work and how it actually works. So now let's say you're given a box with some materials inside weighing 4 kilograms. So we have this box now with a mass of 4 kilograms. And now this box is pushed towards the right. This is the applied force. So there's a young man here pushing the object towards the right. All right, excuse my drawing's a bit out, but it's fine as long as you can see what I mean by positive work. So now this applied force is being applied towards the right. You understand? And now let's say this object moves a certain distance towards the right. All right, the new position of the box is there. Let's say it moves maybe 0.5 meters towards the right. All right, so you can see from this diagram, from these two definitions that I've mentioned here, of positive work and negative work, you can see that this applied force, or this young man is doing positive work on this box because it's pushing the box towards the right, and then the box is moving towards the right. So the work done is in the same direction. The box is moving in the same direction of the applied force. So that's when we have positive work done. You understand? All right. So now with negative work, we can have the same scenario, but now in this case, we have a very rough surface. Very rough surface there. And this means that we're going to have some sort of friction opposing the motion of the object. There's friction there. So now this frictional force is going to do negative work on this object. You understand? Because it's opposing the direction of motion of the object. The object is moving to the right and friction is moving towards the left. So now that's where we're going to have negative work in this case. All right. Let's move on to how we calculate work, how we get the value of work when you're given different scenarios. So now, this work that we're talking about is the product of the force parallel to the movement of the object. Parallel to the movement of the object. So it's the product of the force parallel to the movement of the object and the displacement. So it's the product of force and displacement. You understand? That's what we mean when we talk about work in this case. All right? So now, representing it in symbols, we're going to have W equals to F change in X cos theta. All right, I'm going to explain all these different symbols that we have there, what each of them means. All right, so now here in this case, where W is going to represent your work in joules. Remember to put in the units when you're dealing with these quantities. You understand? And this F is the force applied, or the force that is parallel to the movement. This is very, very important here, because you're dealing with force that is parallel to the movement of that object. You understand? So it's the force parallel to the movement, and the change in X is the displacement. Oh, the force is newtons. Remember to put in the units when you're dealing with these quantities. This is the displacement, and then measured in meters. So it's the distance that the object moves as a result of the applied force. That's your displacement. All right. And now the theta that you see there, theta represents the angle between the applied force and displacement. All right, I'm going to show you how we're going to apply all this when you're solving different examples or different problems involving work, and I'm going to do that in a few minutes to come. All right, I just want to lay down the foundation, give you the basics when it comes to work and energy. All right, now let's move on to the work energy theorem. Okay, this one is very important when it comes to your exams. It's very common in your final exams for grade 12. They can ask you to state this work energy theorem, or maybe they can just give you a question where you require to apply this work energy theorem. All right, so it's very important for you to be able to understand this and also be in a position to apply it to solve different questions. All right, so it's the work energy theorem. Work energy theorem. All right, yeah. So now the work energy theorem states that the net work done on an object. Okay, I'm gonna write it down here with a different color. Is a different color now. All right, so it's the net. It says the network done on an object. I hope you guys can see that. On an object is equals to the change in kinetic energy of the object. The change in kinetic energy, let me just say EK, of the object. All right, so what this means now here is that net work equals to change in EK, which also means that you know that kinetic energy is represented by half mv squared. So final velocity minus half mv initial velocity. All right, it's just the difference or the change in kinetic energy there. Okay, and again, this kinetic energy is measured in joules. All right, measured in joules. Also remember to put in the units when you're dealing with energy and all that. Okay. And also just to remind you guys, kinetic energy is the energy due to motion. All right, energy due to the motion of the object. That's kinetic energy. That's why we're considering velocities there, because it's energy due to motion. Remember, there's a relationship between motion and velocity. Like, velocity is your rate of change in displacement. You understand what I mean? So now, that's the relationship there between kinetic energy and your network done on an object. Okay? So now, just to expand on this, let me just write it down here, show you that's coming from there. So now in this case, where m is the mass of the object. Mass of the object given in kilograms, okay? And now Vf, final velocity of the object, given in meters per second, all right? And now Vi, which is there, Vi, this is your initial velocity, all right? Also given in meters per second. Okay, now this is the work energy theorem. So like I've mentioned before, it's very important for you to understand this and also be in a position to apply it in solving different equation. All right, now let's move on to, just going to expand a bit on energy. That's when I'm going to talk about the principle of conservation of energy. I'm just going to remind you the basics about energy and the conservation of energy, or the principle of conservation of energy. All right, I feel like it's important for me to just expand on this to make sure that you guys have a better understanding of this concept of energy. All right, and also just to remind you guys, this is also a scalar quantity like work. Scalar quantity, so it only has magnitude, so it's magnitude only with no direction. All right, so when you're reporting scalar quantities, you just put in the magnitude and the SI unit. All right, the SI unit is very important because you can be in a position to lose marks if you miss out your SI units. So you need to put in your SI units to make sure you get the maximum marks from that particular question. All right, so now here we don't have direction, so it's magnitude only, no direction. All right, before when I was dealing with kinetic energy, also measured in joules. All right, measured in joules, which is J there. And then now let's talk about the very important principle. And this principle is also very important for you to understand it. All right, because physical science is a subject of principles. You understand? You just need to understand a lot of principles and also be in a position to apply the understanding of those principles in solving different problems. All right, okay? So now this principle now, it's the principle of conservation of energy. All right, of conservation of energy. I'm sure some of you already have an idea of what this principle states from just the title there, which says conservation of energy. So some of you are already calling it out. Okay, so now this principle states that energy cannot be created or destroyed. You can't create or destroy energy. All right, cannot be created or destroyed. Okay, can only be transferred from one form, energy cannot be created or destroyed, but can only be transferred. All right, you can just transfer energy, but you can't create it or destroy it. transferred from one form to another. And guys, please stay with me. I'm going to solve some problems in a few minutes. And it's going to be very, very eye-opening for you guys. You just need to be a little bit patient, because I know some of you guys have already gone through these basics when it comes to work and energy. I'm just reminding some of you who haven't really gotten the grasp of it. You understand? So now, okay, let me just continue with the principle of conservation of energy. So it can only be transferred from one form to another. Okay? Can only transfer from one form to another. For example, you can transfer kinetic energy into or potential energy into kinetic energy, and vice versa. You understand? So you can do that. And also kinetic energy into heat and all that. So you can only transfer kinetic energy. You can create it or destroy it. All right? And also there's another way of stating this principle. You can state it in terms of mechanical energy. All right? And let me just get a different color there so you guys can be able to see it. So under the same principle, you can say in simple terms, the mechanical energy in an isolated system is conserved. Isolated system is conserved. This means that the energy before is equals to the energy after. So like the initial energy is equals to the final energy in an isolated system. All right. I'm going to write an equation to show this, or to show what this actually means. I'm going to write a symbolic representation. Okay. Let me just put in a different page or a new page there. Okay, here. So now we're still under the principle of conservation of energy. All right. Let me just write it here so you guys don't get lost. Of conservation of energy. Still dealing with the same principle, okay? Alright. So now we're going to have this, which is the kinetic energy before plus the potential energy before equals to kinetic energy after plus the kinetic energy or the potential energy after. Alright? That's what we have there. And we've already covered kinetic energy. Let me just try to cover potential energy quickly here for you to show you what potential energy actually is, or how we can calculate potential energy. All right. So it's given by mgh. Okay. So this is your potential energy. All right. And it's the energy. Let me just write it down here. It's the energy due to the height. You understand? Due to the object's height. Energy due to the height. To the height above a certain reference level. Okay? So that's your potential energy. Energy due to the height above the reference level. Or the reference line. That's your potential energy. Okay? And now in this case, where m is the mass of the object, mass in kilograms, and then g is the gravitational acceleration, which is a constant, okay, given by 9.8 or 9.81 meters per second squared, okay, and then the h, that's your vertical height. Vertical height. Okay. And just like potential energy, or just like kinetic energy, its potential energy is measured in joules. Measured in joules. Okay. Now let's move on to the last part of these basics. We're going to talk about conservative force and non-conservative force. Okay. Just gonna give you a little bit of a glimpse of what these forces are all about. Okay. So now, firstly, we're gonna have. Let me get a different color there for you. conservative force. Conservative force. Okay. So now this is the force. The force for which the work done on an object between the 2 points. The work done is independent of the path taken. All right. So if work is done on a certain object between the 2 points due to a conservative force, that means that work done is independent of the path that is taken. All right. So I'm going to give you an example of what conservative forces actually are. Independent of the path taken. For example, let's say you have your gravitational force. This is a conservative force because the work done on an object falling due to gravity is independent of the path taken. All right. Now, lastly, let's talk about non-conservative force before we can start with solving different problems involving work. So a non-conservative force is a force for which the work done depends on the path taken. I'm just giving a brief summary of what this non-conservative force is. All right. Is dependent or depends. Is dependent on the path taken. All right. For example, we have frictional force. All right. Because now work done by frictional force depends on the path that the object is going to take. Okay. Be it a rough surface or a smooth surface. So it's going to actually depend on that. Okay. So that's when we're dealing with non-conservative forces and conservative forces. Okay. So now let's just start solving different problems involving work. And I'm going to show you how we apply the principle of conservation of work and also the work energy theorem. All right. Let's begin. Just going to give you scenarios there. And I expect you guys to write down some notes so that you can refer to those notes when we start answering these questions that are going to follow after those different scenarios. All right. Let me just get a big pen there. Okay, we're given the track for a motorbike. A motorbike track, motorbike race consists of a straight horizontal section. All right. So we're dealing with horizontal surface here. Horizontal section. All right. That is 800 meters long. So we're dealing with the horizontal surface of 800 meters long. All right. And we're given that we have a motorbike there running on a racetrack of 800 meters long. All right. So now this question goes further and says, it says that a participant rides at a certain speed or a certain average speed. All right. Certain average speed. Okay. And completes the 800 meter long course in 75 seconds. All right. So we're given the distance and also given the time. Okay. And let's say to maintain this speed, a constant driving force of 240 newtons acts on the motorbike. So we're also given the force that's acting on the motorbike as it's running along this 800-meter track. Okay. So now the question says, calculate. We need to calculate here now. Calculate. Oh, let me get a different color there. This one here. Calculate. That's the question that we have now. Calculate the average power developed by the motorbike for this motion. Okay. So one thing that I didn't mention here was the issue of power. We didn't get to cover power in the basics that I gave you, but we can just do it now quickly. So now power is the rate of work done. So it's the work done divided by the time. All right. So that's your power. And it's measured in watts. All right. So in this case, we're given the force, we're given the distance, we're given the time. Okay. So now what we need now, we can just solve it systematically. You can start with the work and then use the work to find the power. All right. So now remember, work is equals to the force multiplied by the displacement cos theta, which is the angle between your force and displacement. All right. So now in this case, we're given, or let me just draw a simple diagram here to show you how this scenario actually looks like. Okay. So I'll draw a small bike here. Right, that's a small bike. That's the guy riding the bike there. Okay, well, it's a motorbike. All right, there, and it's going towards that direction. Okay, at a force of, or is applying a force, or they're applying a force of 240 newtons. Okay, going towards that direction. And now the whole track is 800 meters. Okay, so now the force that we're given is 240 newtons. Okay. That's what we have now. And now the distance that we have is 800 meters. Okay? 800 meters. Because it's the distance, or it's the angle between the force and the displacement, which in this case, the force is being applied towards the right, and now the motorbike is also moving towards the right. So the angle between the force and the displacement is 0. Okay, so it's 0 degrees. 0 degrees there. You can just use your calculator quickly there to find out the value of the work done. Okay, it's 240 multiplied by 800 cos 0 degrees. So you're gonna have 192,000 joules. That's the work done. Okay, so now we haven't fully answered this question. We've answered only one part of the question, which has to lead us to the second part of the equation, where we need to calculate or find the power. All right, so we're going to use this work to find the power, or the average power. Okay, so remember, power is given by work, or work done divided by the time. Okay, that's your power. Okay, so now what we're gonna do here, we're gonna take this work, use it to find the power. All right, joules divided by the 75 seconds. Now let's use a calculator quickly to find the power, or the average power for this bike to move from a certain point and travel a distance of 800 meters. Okay, so we're gonna get 2560 watts. Remember to put in the units there, watts. So now that's your power, or the average power that needs to be applied for this bike to move from a certain point and cover that 800 meters. All right, so now let's move on to another question. Okay, I'm gonna give you a scenario again. Get your pens and papers ready there, that you can take some notes. All right, now in this example we're gonna have well, another person. We have another bike now. All right, so we're gonna have another bike, but in this case it's gonna be on an inclined plane. You understand? We're not gonna be dealing with a straight line now, because the first one we're dealing with a straight track. You see, a straight line track. So now in this case we're gonna be dealing with an inclined plane. Okay, let me just give you a scenario now. So now it says another person practices on the same motorbike. So using the same motorbike, but it's a different person now and a different setting altogether. Okay, so it's the same motorbike on an inclined track. All right, so it's no longer a straight line or a flat track now, it's inclined. Okay, so now this person is starting from rest. So they're starting from zero, from velocity of 0, and then building up to a certain velocity. Starting from rest, the person rides a distance of 450 meters. Okay, a distance of 450 meters up the incline. Okay, up the incline. So now this incline, you're given that it has a vertical height of 5 meters. This is the vertical height of the incline of 5 meters. Okay, I'm gonna draw it to make it a bit easier for you guys to understand and visualize it. All right. So now let me just draw it quickly here. This is the drawing of the inclined track. So that's the inclined track. All right, so this guy is starting here at this position. That's where he's gonna start riding his motorbike all the way up the incline. Okay, now this incline 450 meters long, starting from his starting position there at the bottom. Okay, now the height is given as 5 meters. All right, also we're gonna have a bike there, and the guy riding the bike up the incline. All right, so he's applying a force in that direction, or the bike is applying a force in that direction. It's moving in that direction. All right, so now the question goes further and says the total frictional force. So in this case we have some friction there acting on this bike. Frictional force acting on the bike is 294 newtons. Okay, that's the friction that's acting on the bike as it's moving up the incline. All right, and it says again the combined mass of the rider and the bike is 300 kilograms. So that's the mass of the driver and the bike. So it's 300 kilograms, all right? And the force as the bike is moving up or up the incline The force is 350 newtons. That's the forces the bike is moving upwards, all right? So now we also given that we need to consider the bike as a single system. As a single system. Bike are one and the same thing. You understand? So it's a single system that we're dealing with now here. Okay? So now the first question says, draw. We need to draw. Draw a free body diagram. Free body diagram of the system. Of the bike system, all right? So we need to draw a free body diagram of the bike system, all right? So remember, the rider and the bike are one and the same thing. So they make up, together they make up the bike system, all right? So let me just draw a free body diagram here for you. Remember with free body diagrams, you represent the object as sort of like a dot, but make sure it's visible. Don't like put a small dot there. You need to make it a bit visible, all right? And make it easier for your marker, all right? So now in this case, we're gonna have, the first thing we're gonna have the normal force, okay? I'm gonna call it Fn. So that's the force acting in the opposite direction of your gravity. You understand? That's the normal force. And also we're gonna have the applied force. As this bike is moving upwards, all right? That's the applied force, okay? And we're gonna have, let me just draw it on an inclined plane. I think it's much easier if I just draw it on the inclined plane, so you guys don't get a bit confused about that. Okay, this is the inclined plane, okay? So that's where we're gonna have, that's where we have our bike system. Then the Fn. Then we're gonna have the applied force. So now guys, this is just the surface there, the inclined surface. It's got nothing to do with the free body diagram. I'm just trying to show you how this whole thing is inclined, all right? It's just the inclined surface here. Let me just put in a different color there to show you that it's an inclined plane. It's got nothing to do with the free body diagram, okay? That's the inclined plane, all right? Now we're gonna have the force due to gravity. Force due to gravity, okay? So in this case, it's acting at an angle because we're dealing with an inclined plane. So it's acting at a certain angle, all right? That's your weight, the weight of the bike system, all right? And then remember, they told us that there is some friction going on here as the bike is moving upwards, or yeah, as the bike is moving up the incline, all right? So now we're gonna have friction there. That's the frictional force, FF, all right? Yes, that's it now. You have covered your free body diagram, and so you're done with the question. All right, let's move on to the next one. I hope you guys have taken some notes so that you guys can be able to refer to those notes as I progress to the next question, all right? Or the next part of the question. Okay, so now it says state, so let me call it question 2. State the work energy theorem. All right, I just mentioned it not so long ago. I'm sure you guys can recall that. All right, so the work energy theorem, it's the one that says that the net work done on an object is equal to the change in kinetic energy. And remember, in physics, if they ask you to state a certain principle before, just know that in the next question, you're going to be required to apply that certain principle, all right? So you need to be very careful and be aware of this. You understand? So remember, if they ask you this question now, in the following question, they're going to ask you to apply this to see if you're in a position to understand it and also apply it in solving different questions, okay? So now the next question says, use the work energy theorem. Theorem to calculate, you see, you're being referred to the principle or the theorem that we stated above, okay? So you're required to use it to calculate the speed of the motorbike at the end of the ride, at the end of the 450 meters. Of 450 meters. So you need to find the speed, okay? So now using the work energy theorem, this is what we're going to have, work energy theorem. Okay, and also you need to refer to your free body diagram now in this case, because you need to see what are the type of forces that are acting on your object so that you can be in a position to calculate the work done or the net work on that object. All right. So now in this case, okay, let me just draw the free body diagram again so that you guys can be able to see what I'm going to refer to. Okay, that's the inclined plane. I'm going to give it a different color again so you guys don't get confused. That's the inclined plane in green. And then this is the object or the system, the bike system. That's the Fn, the normal force. And then here we're going to have the applied force. Then we have frictional force acting in the opposite direction. And then we're going to have Fg, which is the force due to gravity, okay? So now what we're going to do here is that's the inclined plane in green, okay? What we're going to do here now, we need to find the net work or the total work done on the object, all right? So to find that, you're going to say, okay, net work will be equals to work done by the normal force, Fn, plus work done by the frictional force, okay, plus the work done by the applied force, plus the work done by the force due to gravity. But then with the force due to gravity, we need to consider the component of the force due to gravity that's acting parallel to the movement or displacement. Okay, so now here, because it's on an inclined plane, the force due to gravity is acting at a certain angle, all right? So we need to resolve it into its component. We're going to have the x and y components, all right? There we have it. So now this is the y component of this force, and then that's the x component of this force, okay? So you can just say force due to gravity, x. So it's the component along the incline, all right? So we just need to resolve it. And also, before you can try to resolve it, it's very important for you to know the angles here. All right, so here in this case, we have a right angled triangle. We're given the opposite side, which is 5 meters. And then the hypotenuse is the length of the track, which is 450 meters, all right? That's the hypotenuse, 450 meters there, okay? So now for us to find this angle here, we just need to use sine. So let's call it angle beta, all right? So to find angle beta, we just need to use sine, the sine ratio. Sine beta equals to 5 divided by 450. So it's opposite divided by the hypotenuse, all right? So angle beta will be equals to inverse sine 5 over 450, all right? So that's the angle beta there, all right? So now for us to find this angle here, we just need to say, all right, so now if here beta is this angle here, and here we have 90 degrees here, so we have a small rectangle triangle. So this angle, this small angle here, will be 90 degrees minus beta. 90 degrees minus beta, all right? So it's just small angle here. I'm just trying to show you how we're going to resolve the force due to gravity to its x and y components, all right? That's what we have there. And then from there, you can see that we also have a right angled triangle there, okay? So it's 90 degrees there. And now here, since here we also have 90 degrees again, So it's going to be 90 degrees minus 90. So this angle here, let me call it angle alpha. All right. So it's that angle there. I hope you guys can see that. It's angle alpha. So angle alpha will be equals to 90. Since we have 90 degrees here also, let me just try to use a different color there. See if can be able to. So now here also have 90 degrees here. All right, on this triangle here. So another triangle here where we have our force due to gravity. All right. So for this angle alpha here, it's gonna be alpha equals to 90 degrees. This 90 degrees minus the angle that we have on the other side, which is 90 degrees minus beta. All right. So now we're gonna have 90 degrees minus 90 plus beta. So now alpha is equals to beta. All right. So alpha is also equals to sine inverse 5 divided by 450. All right. That's what we have for alpha there. All right. There you have it. Good. So now from there, we need to find the work done, or the net work done. All right. Going back to this equation here that we have. So work done by the net force. I mean by the net force actually. That's the net work done. All right. Remember, the work done by your normal force is 0 joules. So the work done by the normal force is 0. All right. Because now cos 90 degrees, that's 0. All right. You're going to have 0 there for work done by your normal force. All right. You need to be able to remember that. All right. Because it's always acting perpendicular, or most of the time acting perpendicular to the motion of the object. All right. At 90 degrees. So that's why you're going to get a 0 there, because cos 90 degrees is 0. All right. Now let's move on to work done by the frictional force. Okay. So for work done by the frictional force, we just need to say, all right, so it's the frictional force multiplied by the displacement cos theta. All right. I'm going to put in the values in a moment. All right. And then for the applied force, we're going to have applied force multiplied by the displacement cos theta. All right. The same thing. And then for the x component of the weight of the object, we're going to have Fg, let me call it Fgx, which is the x component. Change in x cos theta. All right. So now at this point, we can substitute, or we can put in the values there and calculate the net work done. All right. So for frictional force, we're going to have the frictional force was given as was given as 294. All right. That was the frictional force that was given. All right. So you just need to put in the frictional force as 294 newtons multiplied by the displacement, which is 450 meters. All right. That's the distance that this motorbike is going to travel from the bottom all the way up the incline. All right. Cos, and then the angle between the frictional force and the displacement is 180 degrees. All right. So you can see from this diagram here that this object is moving upwards the incline, or up the incline. All right. So that's the direction of the motion. And now the frictional force is acting in an opposite direction. That means now the angle between the frictional force and the displacement will be 180 degrees. All right. So we're going to put 180 degrees there. 180 degrees plus the applied force, which was given as 350. All right. That's the applied force as this bike is moving upwards the incline. All right. Or up the incline. All right. There. Okay. So now it's 350, the applied force, multiplied by 450, which is the displacement. And then cos, the angle between the displacement and the applied force is 0 degrees, because the applied force is acting in the same direction as the displacement. All right. It's going to be 0 degrees. Plus, remember now we're dealing with the x component of the weight. Okay? Now we said we need to resolve this triangle there. This triangle that I just drew here, which shows the different components of the weight. So here, I'm going to call it FGX. This is the x component. And then here, FGY. All right, I hope you guys can see that. All right. So I'm just trying to resolve this weight since it's acting at a certain angle. All right. So now we're going to have, I'm going to write in a different color here. We're going to have the weight of the object. Remember, the weight of the object is given by mass times gravitational acceleration. All right. So I'm just going to put in the values there. Let me just write it down here, down below. So the mass of the object or the entire system is 300. We're given here that we need to take the combined mass of the rider and the bike is 300 kilograms. All right. And then we need to consider the bike as a single system. Okay. So that's why we're saying the system or the weight of the system is 300 kilograms multiplied by 9.8, which is the acceleration due to gravity. All right. And then remember, we're resolving this. So now we're dealing with this component here. Okay. So it's going to be sine. Okay. Since we're dealing with this component here on this triangle. All right. I hope you guys can see that. So now this is the hypotenuse. This is the opposite. This is the adjacent. So now we're dealing with the opposite and the hypotenuse. So we're going to use the sine ratio. All right. I hope you guys can understand that. We're just trying to resolve this triangle here where we have the weight. All right. Resolve it into its x and y components. Okay. So it's sine the angle there, the angle alpha, which is given by inverse sine 5 over 45. I mean 5 over 150. All right. So we're just going to put it there. I didn't write the value here because I didn't want to round it because it's going to affect our final answer if we try to round it so many times before we get to the final answer. All right. So I'm just going to take it as it is. Sine inverse. This is the angle, by the way. All right. There you have it. So now that, and then remember, we need to also multiply because this part here, this is just the force. All right. This is just the force. We haven't multiplied with the displacement. So we need to multiply by the displacement now. Okay. Multiply by 450. Cos. So we need to put in the angle now between this. So now, let me just draw it in here quickly. This is acting in that direction. This component of the weight is acting in that direction. And this is acting in the downward direction. So now this component is acting in an opposite direction to the direction of the motion. All right. Because the object, the bike is going up. And now this weight or this component of the weight is acting in the opposite direction. So that means now the angle between this component of the weight and the displacement is 180 degrees. 180 degrees there. All right. So now what you can do now, you're almost done. You just need to use a calculator to calculate the work. For 50 multiplied by cos 180 plus 350 multiplied by 450 cos 0 degrees plus 300 multiplied by 9.8 multiplied by sine inverse sine 5 divided by 450 multiply by 450 cos 180 degrees. All right, let me just do it again quickly. All right, it's 350 by 450 cos 0 degrees. All right, plus 300. Let me put it in the bracket. 300 by 9.8 by sine inverse 5 divided by 450 multiplied by 450 cos 180 degrees. All right, plus 294 multiplied by 450 cos 180 degrees. All right, so now this is what you're gonna get, or this is what you have to get. 10500 joules. Remember to put in the units when you're reporting these quantities. All right, so that's what you're gonna get there for your network. All right, but the question doesn't want us to calculate the network. It wants us to calculate the speed. All right, this is just a way of getting the speed of approaching this question, you understand, and also using a systematic approach so that we can get to the answer. All right, so now we need to find the speed using the work energy theorem. All right, I'm going to show you that in a moment. Now remember, the work energy theorem says that the net work is equal to change in kinetic energy. So we need to use this network to find the speed. All right, so this is what we're going to have, equals to the change in kinetic energy. All right, and now remember, kinetic energy, or the change in kinetic energy, is represented by half mvf minus half mvi squared. All right, so we have the network. We just put in the work that we got here, which is 10,500, and now we need to find the final velocity. Find the final velocity, because the object or the bike is going to start at rest, so it's going to start from rest. That means the initial velocity will be 0 meters per second. All right, that's our initial velocity. So this here will be 0 because it's starting from rest. Starting from rest. So the initial velocity is 0 meters per second. All right, so now that means now this whole portion of the equation is 0, because 0 or any number multiplied by 0 is 0. All right, so we've eliminated this part of the equation. Now we're going to be left with 10500 equals to half, and we can put in the mass of the system, which was given as 300 kilograms. They're saying the mass of the bike and the rider is 300 kilograms. So we just need to put in the mass there, all right, of the system. 300 kilograms VF squared, all right. So at this point, you can use your calculator to find VF, all right. So it's going to be 10500, or you can just multiply by 2 before you actually use your calculator, all right. So now here, if we can just multiply by 2, multiply by 2, multiply by 2, it's going to be 21,000 equals to 300 VF squared, all right. And at this point, you just need to divide by 300, all right. 21,000 divided by 300, 21,000 divided by 300, you're going to get 70, all right, VF squared. So now to get VF, I'm going to take the square root of 70. Square root of 70. Now that's 8.37 meters per second. All right. So we're asked to calculate, use the work energy theorem to calculate the speed of the motorbike at the end of 450 meters. All right. So now the speed of the motorbike at the end of 450 meters is 8.37 meters per second. All right, that's what we have there. And here, remember, okay, yeah, that's what we have here. That's the velocity, meters per second. All right, that's it for this lesson, guys. Thank you very much for joining us, and also be on the lookout for a lot more lessons coming up soon. Also, don't forget to check out our website at www.blendedacademy.co.za, and also check out our social media platforms. We're there on Facebook, Instagram, and also Twitter at Blended Academy. All right, please do check out our pages, and also be sure to like and also subscribe to our YouTube channel at Blended Academy. All right, thank you very much for joining us, guys. Also, please feel free to send your comments or send your questions, and we'll be more than happy for you to assist. All right? Thank you.
Okay, great. Thank you very much, guys, for tuning in today's lesson. We really appreciate your time. I hope that this lesson was very insightful and thought-provoking, and you have learned a lot. So thank you very much from Blended Academy.